Hi, I'm Maya, and welcome back to Chem Mayhem, where I teach you about different chemistry concepts by doing step-by-step practice problems. This is Part C with solution stoichiometry and limited reactions. The first problem reads that we have 0.150 liters of a 0.450 molarity NH43PO4 solution is mixed with 250 milliliters of a 0.5 molarity MgNO32 solution to produce a solid precipitate of magnesium phosphate, whereas for the limited reaction as well as the mass of the precipitate that will be produced and the concentration of each ion. Alright, first step is that we have to set up our rice table. So I'm gonna set it up here. And I'm just gonna write the same equation that we have here. Alright. Now I'm going to balance the equation. See, we have 3 magnesium, 6 NO3. One, 2. Alright, so I'm just gonna fill this in the same way. Alright. Now, looking back at the information we're given, we want to calculate our moles of our initial, since this is all in moles. Using our formula, we have liters and molarity. So what we want to do is calculate moles. All we have to do is rearrange it. So all we have to do is times liters times molarity to get our moles. So we're given 0.150 liters times a molarity of 0.45 molarity NH4 3PO4, and we get 0.0675 moles I'm going to write this in our table. Since products don't have any, I'm just going to cross them out. Now I'm going to calculate the initial for our MgNO32. So because this is in milliliters, I have to convert it to liters. All I have to do is divide it by 1,000. I get 0.25 liters times 0.500 molarity MgNO32. So I'm gonna multiply that. And I get 0.125 moles of MgNO3 2. So I'm going to fill this out, 0.125 moles. And now we can move on to our change. Our change correlates with our subscripts when we balance the equation. So our change for this would be negative 3x, this will be 2x, this will be plus, because these are products, 1, and then plus 6x. Alright, now for our end, we have to calculate our limited reaction, finding the x. So with these subscripts, we have to set up an algebraic equation and see which one will be smaller in the end for our limited reaction. So, because this correlates with 2, just got our subscript and take it and divide it by 2. I get 0.03375. And just to make sure, I'm gonna do the other one. Divide that by 3. I get 0.0416. Because this is smaller, this is our x. Thus, meaning NH4 3PO4 is our limited reaction. And yeah, so this means that this is our x. So now we just have to calculate how many moles of our MgNO3 that we have extra. So I'm going to take my x and I'm going to times it by 3. Times that by 3, and I get 0.1025, and then I'm gonna take that from our initial and I'm gonna subtract them and find the difference. So I get 0.02375 moles. And for these products, all I have to do is plug in my x. So this would just be 0.03375, and this is just x times 6. So I get 0.2025. Alright. Now, part 2. We're asked for the mass of the precipitates that will be produced. Because this is labeled as a solid, the Mg3PO42 is labeled as a solid. Here, we know that this is the precipitate, so the mass is 0.03375 in moles, but we are asked for it in grams because mass is measured in grams mostly. So all we have to do is transfer 0.3375 moles of Mg3PO4 to grams by going from moles to grams. So 1 mole of Mg3PO4 2, and our molar mass is 262.84 grams Mg3PO4 2. And when we multiply those across, we get 8.87087. With sig figs in mind, it will be 8.87 grams Mg/PO4 2. So alright, now that we're almost done, we just have to solve for part 3. It says calculate the concentration of each ion remaining in the solution. Looking at our equation again here, we know that this is a limited reaction, so there will be none left. So we do not have to calculate that, as well as the precipitate, because it is a solid and it does not produce any ions. So we're left with MgNO32, and we're left with NH4NO3. So we have to break these ions apart. So I'm just gonna write them here. Okay, so we know that we have 2 of these NO3s because of this over here, and then for the Mg we have only 1, and for our NH4NO3 we have 1 NO3 and 1 NH4. Pause. Alright, now that we've broken them down, we have to use, this is where solution stoichiometry comes into play. We have to use a mole-to-mole ratio to get each ion alone. So because we have our mass here, I'm going to start with Mg. We have our mass here. We have a mass of, taking it from our end, so we have a mass of 0.02375 moles MgNO32, and I'm gonna times that by moles Mg NO32, and it'd be by 1 because there's only 1 produced. So we know that with it just being 1 on both sides, there's nothing really being done, but I just wanted to show the process. So we get 0 point, and these cancel out, and we're left with, oh my bad, I just want to do Mg. So we're just left with Mg because that's what we canceled out these. So we're left with moles Mg2. So now we have to, because it's asking for our concentration we remember is a bigger name for molarity, and molarity is always moles over liters. So I'm just gonna write our formula over here, moles over liters, and So now we just have to look back into our problem, and we see that our liters was given to us in the beginning. So it would be 0.150 liters plus 0.25 liters. And when we add those together, we get 0.4 liters. And this is what we're going to divide by to get our concentration, because this is our volume. So when we do that, we get 0.059375 moles of Mg. All right. Moving on. We can solve for our NH 4 that we have, and using the end of this, we have 0.0025 moles of NH4, because it would be similar to a 1-to-1 ratio, just like the one we did before. I'm going to skip that step and show you that this is our end result, just from knowing our end of how much we had there. So I'm just going to divide that by 0.4. And I get 0.50625 molarity of NH4. Alright, now that we have, this should be molarity. Now that we have the molarity of Mg and NH4, all we have to figure out is the molarity of NO3 of both of these. Since there's 2 here, we have to use the subscript, and so it'd be 0.02375 moles of MgNO3, 2. And we want to cancel them out, so moles of MgNO3, 2. And this should be 2, because 2 of NO3s are produced in this equation. So we have to times our we have to times 0.02375 by 2, and we get 0.0475. All right, and now we have to divide that by by 0.4, which would be 0.11875 molarity for Mn3. However, we are not done. We still have to calculate it for our compound NH4NO3, and because we have 1, we know that it's just the initial value, just the N value that we have, excuse me. So it would just be the same as how we did NH4. So similarly, it would be 0.2025 moles of NO3, and we would divide it by 0.4. So I get 0.50625 molarity of NO3. And so all we have to do is add these together, the 0.50625 molarity and the 0.4 or 11875 molarity to get a total, which we get 0.625 molarity Mn3. So with sig figs in mind, this has already sig figs, so 0.625 molarity Mn3. And this for our Mg, sig figs would be 1, 2, 3, so it would be 0.0594 molarity Mg2 with the electric charge. And lastly, with our NH, there is 1, 2, 3 sig figs, so it would just be 0.506 molarity NH4. And because there was no PO4 and none left in the equation, the result would be 0 molarity PO4.